Hi, and welcome to the sixth and last lecture of the control course. Today we're going to talk about model predictive control. So model predictive control is an optimal control technique. So before introducing what model predictive control is and what it does and all of its specification, we're going to talk a bit about optimal control. So what is the motivation behind optimal control? Well, the main motivation is that we want an objective-based design. So basically what we were doing before, so what we did so far until the fifth lecture, was that we have a generic goal. We want to reach zero error, or we want to park the car somewhere, or we want the bicycle to be stable and not fall down. With the objective-based design, on the other hand, we have like a slightly different control problem where we want to minimize a cost function. So we want to achieve something. And this can be anything, can be again minimal error, but it can also feature stuff like minimal actuator effort or other things like this. And also, optimal control is, since it's an optimization problem, it can be a constrained optimization problem. So optimal control can feature constraints. You can explicitly put constraints in the control problem. And again, these constraints can be on actuators, because you don't want your actuator to be overstressed, for example, or it can be on, for example, the reachable states. So maybe there's an area where the robot or whatever system you are controlling cannot go, and so on and so forth. Also, optimal control inherently has the property or the idea of predicting the future state, because in order to have the optimal strategy to tackle a certain task, to deal with something, it has to have embedded somewhere the prediction of, okay, what's going to happen afterwards. So if I do this and not this other action, I need to know why I'm doing it, because there's a prediction of what happens in the future. Also, this kind of strategy is something that gives us robustness to variations. So all of the problems that we've introduced so far of noises, disturbances that can happen and can affect the system, and it's something we cannot model, something we don't know. This is something that is usually well handled by optimal control. So these are the main advantages coming from optimal control. So basically, optimal control tries to answer the questions how to best control the system. And by best, we mean something we have to specify in the cost function. So we have an idea of what best means for us, and we want to achieve that, to maximize this goodness for the system by solving an optimization problem, an optimal control problem. Now, let's also go with an example, like, so that it's a bit clearer what's happening here. So we have a model of dynamics of a system. For example, we have that a certain state depends on the previous state and the input that is applied in that state. And it's something that we've already seen. We have some control inputs that steer a certain dynamics, and it affects the state trajectory. So in this case, it's a car, but it can be, obviously this is just an example, it can be anything. So this is what predicts the evolution of the state. So it's this prediction we've been talking about, and we want to control the system. And then the main thing that we want to take care of is that the car, imagine it's an autonomous car, you set a certain goal, and so you want to not have any error. So you don't want to deviate from the reference. This is something we've seen, it's trajectory tracking. And yeah, the problem is we have a certain error, which is the actual state of the car how far is it from the reference, from the trajectory that we've given the car. So we are taking all the errors, and we've seen this with the PID control, but how do we deal with something like this with optimal control, and why is it useful? Well, with the PID control, we know that we can achieve something that gives zero error, so the trajectory would be eventually perfect with no states, with no error, with no error on the after the transient, but we cannot do anything else. There's no other specification that we can give the system. Well, in this case, for example, the objective function that we want to minimize can be something like this. So it's a certain function, so it's a certain cost of our trajectory, and there is a steady state error. So steady state after a transient, we want the error to be zero. So we want to so asymptotically track the trajectory, and with no mistake, with no error. Good. This is something that we know, as I said, we can achieve with PID control. But also, I want to minimize this thing. And now notice that this is the input. So the R and Q, just for now, they're just matrices. So U is the input that is given to the system. So we want to minimize also the input. So basically we are trying to have zero error by having a low actuator effort. And notice that this is a cost function. So it's something that gets minimized. Hence we have this shape, this is a quadratic form. So when Q and R are positive definite matrices, this is minimized by error and input going to zero. So this is basically the optimum that we would like to reach. No error and basically no actuator effort. Of course, this is a cost function. So cost function is different from a constraint, meaning that you shouldn't take for granted that we will have zero error in the end. This is like a compromise between the things, and it's trying to minimize this function. So we're trying to minimize the error, we're trying to minimize the control input. So the result of the control problem will not be maybe as perfect as in the PID case, where we know that the integral action brings the steady state error to zero, but it will be a minimization. So there might be some residual error. So this is the concept of the minimization of something. So we will not have for sure error going to zero in theory. So this is the cost function. And now we said we can also handle constraints. Well, as I said, the constraints can be the two main kinds of constraints. One, it can be the actuator effort. So we know that we cannot go above a certain acceleration. Like we wouldn't be feasible because the actuator we have, the motor we have, doesn't allow it. So this is a constraint that, for example, in the case of the PID, we know it's very dangerous because we know that when we saturate the control, the actuator's signal, we could get into the wind-up problem. Well, we just have a constraint that says, well, you cannot go beyond that. This is the best you can do. This is the stronger you can do something, the most powerful you can accelerate or anything. And also the other kind of constraint can be, there's some area where you cannot go. This is forbidden area. You express the constraint in mathematical form, and then will be just integrated in your optimization problem. So quite easy to handle constraints like this. So basically the optimization problem will be something like, we want to minimize the cost of a certain trajectory, which is of course a feasible trajectory, because we want to find a feasible trajectory for our system that does not violate the constraints. And of course, this is in terms of a trajectory, so for an autonomous car or a robot moving around, but it can be any control system that you're dealing with. So we want to minimize a certain cost function, and we have some constraints. And these constraints are exactly constraints we've seen so far. This is the dynamics. So we have a cost function, it is the trajectory, for example, but we also have to respect our dynamics. We have to have a system evolving in a certain way, because this is the system we have. We cannot have that the solution coming from this is just states going the way they want, because this wouldn't be feasible. This thing falls into the dynamically feasible trajectory. Has to be the system that you're trying to control, of course. So we have to enforce that. Then there's the actuator effort. So as we said, for example, to deal with the saturation. Then if there's some state which is not available, so as we've seen before, where there was the circle and there's the area where the car can go, and in the end we have an initial state. So we want to do all this by starting from here. This is how the optimization problem is set up. How do we solve it? Well, typically there is no closed form solution, and there are tools for solving this. One of the most common ones is Casadi, which is this tool, this library in many languages, and this is a Python example of a Casadi optimization problem. So imagine we have an optimization problem like this, where we have a certain cost function and a certain number of constraints. The equivalent in Casadi would look like something like this. So you start the optimization problem, you just say that you want to solve something, then you start adding variables. So you specify what your optimization variables are, which are exactly the ones that appear in the cost function. And then you say, okay, I want to minimize this cost function, and I'm saying the cost function is subject to a certain number of constraints, which are here, which are exactly the constraints you find there. And in the end, you say, okay, I want to use a certain solver. We won't talk about solvers here. There's a lot of literature around solvers. It's not really in the scope of this course. So this is just take this for granted. This iPopt is one of the solvers you can find. And then you say, okay, solve the problem. It will be an iterative problem, an iterative process. In the end, you will get a solution. And this is a numerical way to get the solution. Now, sounds easy, but there's always some errors. So as we know, the prediction model will always be wrong to some extent. What does it mean? It means that we have a certain model, for example, the dynamics that we've put in the constraints of the previous optimization problem, but that's not enough, because sometimes there are some disturbances acting on the system, and so dynamics is slightly modified, or there's some noise, or there's some, for example, noise in the sensor reading, so the closed loop is a bit altered, or maybe there's noise in the actuator, so we compute a certain actuation signal that we have to feed the system with, but that's actually altered. So we're not feeding the system with what we've computed, and so stuff changes. So the prediction model will always be wrong, and there will always be errors. An error causes deviation from what we would like to achieve. So we have a ground truth, for example, this ground truth trajectory we want to follow, but since we will have some errors that can be of any of these things, then we have a prediction which is a bit off. And an example of this was in the PID controller lecture, when I mentioned, imagine that you have this robot that is moving, but then one wheel is more inflated than the other wheel, and so there's one dominant direction. And so you compute the perfect actuation signal, you feed it to the robot, but the model of the robot, the actual kinematic, the actual model of the robot is not exactly what you think you have, and so basically the behavior is a bit divergent, is a bit different from what you would expect. And this is a big problem, especially we have this optimization problem that look ahead, try to look for the best solution, for the best way to deal with something, and they have a certain control horizon. So they are looking ahead for a certain time, and they are computing the best way to reach a certain state. And especially when the horizon is very long, so imagine you want to follow a whole trajectory and go back here, so the end point is exactly the same as the starting point, and maybe the trajectory is quite long and involved, then this can cause a lot of problems, because if we have a bit of divergence, because the model is not perfect, because there's some disturbance or some noise, this starts diverging, and in the end you will get something that maybe has a similar shape, but then eventually ends up somewhere completely different. So optimization like this would be basically intractable. So you could still set up the optimization problem, solve it with Casadi, but then the solution you will get is not aligned with your expectation. So we have to modify something. And here we have model predictive control. So this is basically where model predictive control comes into play. Why? Mainly because it has one crucial concept, which is called receding horizon. This receding horizon is something that basically tells you, I'm not looking at the whole trajectory and trying to optimize everything. I'm looking at the chunk of the trajectory. So I know that I have to follow something. I'm looking at just the first chunk. So let's say that we have 1 kilometer trajectory and we're looking at the first 100 meters, for example. This is just random numbers. Then I compute the control on different time instance. And let's say that the first control action that I take for the first time step just drives me for 10 meters, for example, of this 100 meters chunk. Then I apply that first one. I don't apply the following ones. Once I apply the first one, I replan. And in this way, you start from the current state, which is something we want, of course. You have a very limited preview of the future, but still is limited, but it's shorter than the whole trajectory, so it doesn't make it super hard to solve. And then you replan every time. And by replanning every time, you can basically correct and you basically address all of the errors that might have happened. But this time, the errors that might have happened just for one time step, which is very short, and it's something you can easily address. So basically, a schematic view of this is, imagine you want to follow this whole trajectory. Before, we've seen something that was trying to solve it all together. Now we're just trying to solve it for this small chunk. And then once we find the optimal solution for that chunk, we apply the first one. You see that we haven't reached the end of the chunk. And then we plan again. And we obtain the optimization for another chunk. And so on and so forth. So now we are able to account for errors, as I said. So you find out immediately if you have a disturbance or a noise acting on the system and you end up in a place which is slightly different from where you were supposed to be, you find out immediately and you can account for it in the next optimization step. And the problem size is reduced. So you're not looking at the whole trajectory and having to optimize all this big monster every time, but you can just look at the very short chunk, and so the process is a bit faster. You don't have to solve the whole problem all the time. So the algorithm looks like something like this. You get the current state, you solve the optimization problem with a certain cost function, a certain dynamics, with a certain initial state, and with the inputs that you have basically the input that basically what you compute. So this means that you compute the first things, and then you apply the first, you get the first, you apply it, and you re-optimize it. So then you forget basically for all the other time steps, which is not the first one. And in the end, what you will get is something like this, where you will have basically this trajectory following. So the blue is the reference. The closed loop solution is the one that you see in orange, and you have this prediction that you see that sometimes it's not perfect, But then in the end, you just apply the first chunk of it. So this is not really a problem. How do we design a cost function though? Because this seems to be the most important thing. Well, the cost function is something that really depends on whatever you want, whatever you need. And it induces your optimal behavior. So whatever optimality means for you, that can be your cost function. For example, in this can be deviation from a reference. We have a certain reference, we have a certain trajectory, we want to follow it. And this is the trajectory, basically trying to address trajectory tracking. Another thing can be maximizing progress inside track bounds. So basically going as fast as possible, not in terms of velocity, but in terms of space. So like advancing as much as I can. And so we have a different solution in the end, a different optimal solution. So the design is really up to you and whatever your system needs, because it's really then it really depends on the kind of system you're designing, you're trying to control. What about the prediction horizon? Because this is also another parameter that you have in your optimization, as you've seen in the algorithm, that's pseudocode of the algorithm. There was a certain time frame t, which you compute the control for. Then you take only the first one, but you're looking at a certain time window. And then we have to decide, okay, how long that time window can be. And it's really up to you. You don't want it to be too long, because as we said, it would make the problem untractable. And in the end, after a while, it will just accumulate errors that you cannot know that they are there once you start. So it doesn't really make sense. But it can also not be really too short, because the short predicting horizon, of course, it reduces computation, so it makes everything faster, it makes everything like you can do more computation and be like having a real-time controller, and which is as fast as you can get. But also it induces a myopic behavior. So in the end, it will try to optimize for something without really knowing what's happening ahead, and so without really knowing how to address something like this. For example, here there's a curve, so you are supposed to turn at some point, but if you have the prediction horizon which is too short, once you solve the problem in this step, you don't know yet that you are going to turn eventually. So this is something that this induces a myopic behavior, because then maybe the car will just be controlled in such a way that, okay, we have to go forward. That's all we know so far. And at some point we will realize, oh, actually we had to turn. And so now we have to do a sharper turn in order to not go out of bounds and not go out of the path, basically. So it can be unsafe. It can be a problem. So this is something we have to address. And one way to address it is, of course, not having the horizon too short. The other way to address it is also to include something in the optimization that tells you, okay, let's make it as safe as possible. So I know that they have a very short horizon, so I know that basically after this there might be a turn, I don't know, and this might cause problems. So let's make a prediction, let's make an optimization in such a way that at the very end, so at the end of the prediction horizon, we want to stop. So basically we are solving an optimization problem where we have to compute a certain number of controls in such a way that the car stops at the end of the horizon. Well, it won't really stop in the end, because as we said, we will apply only the first input and then we will recompute everything. But this is a way of addressing the problem of a short horizon, because even if here's turning, like, we know that we want to stop. So basically all the optimization is driven towards, okay, we have to slow down after the first optimization steps, because we know where we want to stop afterwards. So this helps with this safety measure and dealing with the myopic behavior that can come from a short horizon. Okay, now this was a bit of an introduction basically to what is a control problem, what is a model predictive control problem, and also talking about cost functions, constraints, and all these things. Now let's talk a bit about how to solve an optimal control problem like this. Before starting with the model predictive control, which is a bit harder, it's a bit more difficult, it's more of an advanced topic, we start with something simpler, which is called linear-quadratic regulator. So model predictive control and linear-quadratic regulator are somehow cousins. So the linear-quadratic regulator is a special model predictive control with linear dynamics. So the dynamics of the system is linear. We have a linear system, we're dealing with a linear system. We have a quadratic cost function, so it's a linear quadratic, and we have an infinite horizon. So we are now forgetting about all the good things that we've said about having a shorter horizon, about not having to deal with a huge horizon that has to solve the problem all the time and everything. We are now dealing with an infinite horizon. So imagine we have an optimization problem like this. So we have quadratic cost functions. So these are two terms, and they are both quadratics. So these are quadratic forms, one in x. So we want the state to be small. State can be anything, can be, for example, if you think about the bicycle, the state was, for example, angle phi, so the tilting angle. So we want the tilting angle to be as small as possible. Makes sense. But x can also be an error or can be anything you want. And we want u to be small. So this is also another quadratic form. And when q and r are positive definite matrices, we want them to be small. So we want to achieve something with the smallest amount of control needed. So the smallest amount of control effort needed. What are our constraints? We have a linear dynamic. We have a certain initial state. And as said, we have two symmetric positive semi-definite matrices in such a way that since they are positive semi-definite, these are basically you can imagine it like in the space as balls, and the optimization point would be actually at the vertex. So we have the forward simulation of the linear dynamics we have. This is something that we have already seen with discrete time system, which basically is the reason why we did a discrete time system before too, because as we've been seeing now, everything is in terms of intervals. So we are applying the controls for the first step, and then we are predicting more, or we are trying to optimize step by step, and now we have this forward simulation. So everything we've been seeing in here is based on discrete time systems. So we do this forward simulation that we've already seen for discrete time systems, and we can rewrite it in matrix form like this. So this is just basically rearranging everything in matrix form. So we have all the states, we have basically dynamic matrices. Everything depends on the initial state, so we don't have any other state in here. And then we have all the controls. So basically, this is something that says if there's no disturbance, there's no noise, there's nothing external happening, all the states can be described by the initial state and all the control that we've been applying to the system, which somehow makes sense, because imagine that you have a perfect dynamic, so you know exactly how something behaves. You start from somewhere, you apply a certain input, you obtain the new state. Then you apply another input, you obtain another state. But now it's only on the inputs. The only state you need is the initial state. So this, like intuitively, it makes sense from what we know so far. And we can rewrite this in big matrix form, where all the vector of states depends on the initial state and on the big vector of inputs that we've been applying to the system. Also, we define the stacked cost matrices. So we just stacked this Q and R matrices that we've introduced in the optimization problem. And we can write the cost function in this way. So in the cost function that we've seen in the problem, it was basically the same form, but with the generic X matrix Q and generic U matrix R. Now we're just saying, let's put all together. Let's, like, since we know that everything can be expressed in terms of the initial state, we put all together and we say, I want to minimize basically all of the states, and I want to have the lowest control effort as possible in all of the control instances. So eventually, we can just basically eliminating by all state variables, we have this big cost function, and now it's the stack of everything, and we have the dynamics. So this is the forward dynamics coming from the discrete time system. Now, when we substitute everything, so mainly we substitute this X inside here, you can do the computations. This is what we end up with. So you realize there's no X anymore because we got rid of X with this formula. So everything is in terms of either the input or the state and the input. There are some, these are not constraints, this is just like how the matrices look like. So this is basically just a matter of doing the substitutions in here. You see that there's no, this C still depends on the initial state. So there's nothing disappearing. Everything is either in terms of the input or in terms of the initial state. So we have this new cost function here with matrices that are defined in a way like this. And the important thing that you have to remember about this is that X init is known, is a number, in the sense that it's something that is there, is known, is not something we need to optimize, it's something that is given. H and F do not have neither U nor anything else. C is only X init. So it means that basically here we have the U here and the U here. And U, the input, is the only thing that we can optimize. The only thing that we can optimize and we can compute what's the best thing we can do is the control input. We're not controlling the states, or like we would like to, but indirectly from the input. So U is our optimization variable. And this is the cost function that we're dealing with. And this cost function is quadratic, convex quadratic in U, because H is positive definite, and the positive definiteness of the matrix H comes from the positive definiteness of other matrices that we've seen before. So now this is something we can solve. This can be solved for zero gradients, means we have a center function, we know that it's optimized, that the optimization variable is U, so we can do the partial derivatives with respect to U, and we get something like this. So the 2 comes from the fact that this is in the end a quadratic form, as I said. So like the differentiation, time differentiation works in the way of the time differentiation of scalar functions, but just here we have matrices, and then we have this. So basically with this we can compute U, and U is computed like this. So we have to invert matrix H, and we have to multiply by X init. So this is the final control law that we obtain for the linear quadratic regulator. This is a matrix inversion, and it's a big matrix. The dimension is given by the number of states. So again, the problem of having a very long horizon comes back, because now we have to invert a matrix which potentially can be huge. And this is something that is hard to do, our computers don't like. But it's what we is what we get. This looks like, apart from this problem, this looks like something familiar, because in the end, it's basically a proportional controller. Like, we're just saying all the inputs, all the input signal that I'm giving to the system in every time step is a proportional action from the initial state. That's good. So does it mean that it's solved? Well, we haven't really addressed something. We haven't really said something. This thing might not be stabilizing. There's nowhere where we've said, or we're setting the eigenvalues, or we're looking at the eigenvalues of the system. This we don't know. So this is something that has to be designed accordingly, because the stability depends on the matrices that you were dealing with. Because in here, there are all the matrices that you have, and so you have to basically design that in such a way that this control action is stabilizing. And remember that you have power over these matrices because you are setting the cost function, you are setting the constraints. So it's something you can control, it's something you can tune in the way you need. But it's something you need to take care of, because as of like this might not be stabilizing. So this is basically the batch linear quadratic regulator approach. So first we eliminate all of the state variables. So we have an unconstrained problem only for controls, and the only thing that we have for the states is the initial state, which is known. It's given and we don't have to worry about it. It can be solved analytically. We found the formula, we found the equation for it, and it is basically a proportional controller in the initial state. But it requires to invert one very big matrix, which is something hard. So this is a summary of how the batch LQR works. Now, what happens with constraints then? Well, constraints are usually in form like this. So there's something that can depend on both states and inputs, or something that depends only on states if the state has to be bounded somewhere. So imagine you have many of these. We just stack them all together. We put them in the same matrix formulation, and we obtain like something like this. So we have something for sure will include the initial state, something that includes the states, and something that includes the inputs. Of course, this can be block matrices such that you will have a part of this that depends only on the states, and this disappears. A part of this that depends maybe only on the input, and this old part disappears, and so on and so forth. And this C can be anything. So we have, this is a batch formulation of all the constraints that we want to deal with. And again, we can substitute our dynamics, so our forward dynamics, inside here and express what we're dealing with in this way. So the forward simulation will be something like this, and in the end we end up with a formulation which something that depends on the states, something that depends on the input. And again, like since we have that the states is expressed in terms of the x init and of the input, in the end what we get is just a matrix multiplying x init and a matrix multiplying on the input. And that's it. There's nothing else. This handles all of the constraints that we want to deal with. So basically, back to what we've seen before with the linear quadratic regulator, we have something like this. We have the big cost function where there's the input with their big matrix, also all the stacked input. We have the term that is state and input, and we have C, which is the term that was basically a quadratic form in the initial state. And we have this big chunk of this with this batch of constraints that include the states and the input if necessary. We need to solve this. For this, there is no analytical solution, and it's usually solved with something called quadratic programming. So quadratic programming is a way of handling optimization problems. So more in details, quadratic program is an optimization problem in this form. So there is this, and there is a certain constraints. So if you can already see the similarities between this and what we've seen in the previous slides. So here we have the quadratic form, which might be a quadratic form, for example, in the inputs. Then there's another thing that is basically C, so a certain vector, known vector, that multiplies, again, the optimization variable. And this is basically what we had also, multiplication between x init and u, because, again, I repeat this because it's very important, x init is not an optimization variable, so it belongs in here. And also, there's this linear form of the constraints, which is exactly what we had before. So there was this term in x init, which again falls into this because it's not something we have to optimize. And then there was the input part. This is quite nice as a shape of an optimization problem because there's a theorem that says that if Q is positive definite, then we have one solution, so the solution exists, and it's unique. There's no alternative. Why? Well, this shape is, again, the bowl that I mentioned before. So imagine that the space that you're seeing here is just a very big bowl and goes at the tip of this bowl, so at the lowest part of the bowl, is this unconstrained minimum, is the minimum of this function, and is basically the zero, the minimum at zero. So when the optimization variable is at zero. So imagine that you have this big bowl, which ends here in the unconstrained minimum, which is the zero. Then we have this bowl is described with this level set constraints. So the cost function, sorry. So each of these lines, each of this circle, it basically gives a different level for this bowl. And then ideally we would like to go here. So ideally we would like our optimization to somehow make the state go into here. Fortunately, or make our input actually, because we are optimizing for the input, so make our input go here. Fortunately, this is not always possible because we have some constraints. So imagine that you're doing a trajectory tracking and you want your car to steer following some trajectory. Of course, you cannot reach a steady state where the input is zero because you still need to drive the car, right? So unless you are trying to park it where eventually the car has to stop and there's no input anymore, you still have to move it. So there are some constraints that won't allow us to go here. But then the constraints in this shape especially means that basically we are cutting a sort of polygon in this bowl. And this polygon, of course, because of this shape, because of the shape of this equation, will have a minimum, will have a constrained minimum. So there will be a point in this, and there's a unique point, which is the closest one of all the admissible points to the unconstrained minimum. So that one is the constrained minimum, is the best state that we can reach, is the best solution that we can reach. The optimal control sequence that we get from this, so that we get from this optimization in this bowl, is linear if in the state if the problem is unconstrained, is non-linear if the problem is constrained. And again, we are dealing with model predictive control, so remember, you apply the first one. You don't apply everything that you predict after the first one, you only apply the first one. So this is something is again called quadratic programming. It can also be solved with tools like Casadi and the others that are mentioned before. So it's something you have to numerically solve numerically solve and just basically code and find the solution. So we made it to the end. As a recap, we have introduced a bit of optimal control. So basics of optimal control, the idea behind optimal control, and what are the objective functions, what are the constraints, and also what are the idea behind the objective function, how does it work, and what it means to add constraints to a certain problem. Then, after talking about the time horizon and why it makes the problem difficult, we talked a bit about model predictive control, linear quadratic regulator for solving it, and then quadratic programming in the end. So this is a bunch of references, mainly for model predictive control and optimization in general, which might be useful. On this also there is tons of material from numerical optimization to advanced control methods that you can find online, and many good resources. Here are some that I used for these slides. And this is it. This was the last lecture of the control course. I hope that you enjoyed it, and thank you for your attention.